In a quiet room, a simple magnet lifts a paperclip from the surface of a desk. The motion seems trivial, almost childish in its simplicity. Yet what just happened defies an entire planet. That small piece of metal, pulled upward by the whisper of electromagnetic attraction, has overcome the combined gravitational pull of Earth itself. Every atom of our world pulls downward on that paperclip, and still the magnet wins. A single human hand holding a sliver of iron can overpower the gravity of an entire planet. This is the most striking demonstration of how weak gravity truly is. Physicists have long compared gravity's strength with the other fundamental forces that govern the universe. Electromagnetism, the strong nuclear force, and the weak nuclear force. The differences are staggering. If electromagnetism were represented by the strength of a mountain, gravity would be the faint ripple of a leaf falling upon it. In scientific terms, gravity is about 10 to the power of 38 times weaker than electromagnetism. It is a number so immense that even language strains to express it. Yet this weakness is not a flaw in the fabric of nature. It is a mystery that cuts to the heart of physics itself. Why does gravity, the force that binds planets and sculpts galaxies, seem so feeble at the atomic scale? Why does it fade into insignificance when compared to the invisible hand of electromagnetism that holds atoms together and drives every spark, every flash of lightning, every pulse of light in the cosmos? This question forms the essence of what scientists call the hierarchy problem, the immense gulf between the strength of gravity and the other fundamental forces. For decades, physicists have sought a unified description of nature, a single framework that could link gravity to the quantum fields governing the subatomic world. But every attempt stumbles against this same barrier. The mathematics that explain the electromagnetic and nuclear forces refuse to yield to gravity's strange behavior. Einstein's theory of general relativity describes gravity as the curvature of space-time itself, an elegant geometric truth that has passed every test of observation. Quantum theory, on the other hand, describes reality as a dance of particles and probabilities. When these two systems are brought together, they clash violently, producing infinities that make no sense. It is as if gravity speaks a language that quantum mechanics cannot translate. For many years, physicists assumed that gravity was simply too weak to measure meaningfully at small scales, and that its faintness was a sign of its simplicity. But in the late 20th century, a new possibility began to emerge. One both strange and beautiful. Perhaps gravity is not truly weak at all. Perhaps it only appears weak because it is spread out, diluted across realms that we cannot perceive. To understand this idea, imagine standing beside a beam of light that travels through fog. The light appears soft and diffuse because it is scattered in every direction. Yet if the same beam were confined to a narrow path, it would burn with blinding intensity. In the same way, gravity might be dispersed, leaking out into dimensions that extend beyond our familiar three-dimensional world. We feel only its faint echo, the residue that remains confined to our universe. If that is true, then the weakness of gravity is not a failure of nature's design, but a clue. It could be the key to a deeper structure of reality, one that hides just beyond the edge of perception. For now, we live our lives bound to 3 dimensions of space and 1 of time. Every direction we can move or measure exists within that framework. But what if there are more? What if the universe is not merely vast, but layered? A multidimensional fabric whose hidden folds shape every particle and every star. To follow this path of reasoning, we must venture beyond the limits of human intuition. We must step into a geometry where space itself can twist in unseen directions, where the true architecture of reality may be written not in 3 dimensions, but in 5 or 10 or even 11. It is in these higher dimensions that gravity may finally reveal its secret, not as the weakest force in nature, but as the most expansive one, spreading its influence through unseen corridors of space. And so, To understand why a paperclip can defy a planet, we must first understand what it means for space to have more dimensions than the ones we see. Gravity's weakness is not something we notice in daily life. We feel its pull every moment, anchoring us to the ground, guiding rivers and moons, shaping the paths of planets. Yet this same force that sculpts the motion of worlds can barely hold together 2 grains of sand. Its dominance on cosmic scales comes not from strength but from persistence. Gravity never cancels out. Every bit of matter pulls on every other bit, endlessly, without opposition. Electromagnetic forces can repel as easily as attract, but gravity only accumulates. Over billions of years, its patient hand has gathered the dust of the universe into stars, galaxies, and clusters of galaxies stretching across unimaginable distances. If we could somehow stand outside the cosmos and compare the fundamental forces, we would see something astonishing. The strong nuclear force binds protons and neutrons together inside an atomic nucleus, but its reach extends only across a distance smaller than a trillionth of a meter. The weak nuclear force governs radioactive decay, fleeting and local. Electromagnetism stretches farther, shaping chemistry, light, and magnetism across space. But gravity never stops. It weakens with distance, following the inverse square law described by Newton centuries ago, yet it never truly reaches zero. It threads through everything, unending, eternal. And still, when physicists try to unite gravity with quantum theory, the numbers refuse to cooperate. The strength of gravity measured between 2 elementary particles is absurdly small. So small that if you magnified their electromagnetic attraction to the scale of a roaring ocean, their gravitational pull would be fainter than the ripple of a single drop. To make the mathematics of unification work, scientists must imagine why gravity's true energy seems hidden from us. The great dream of 20th century physics was the grand unification. To find a single equation describing all forces of nature as manifestations of one deeper reality. Maxwell accomplished the first step in the 19th century, showing that electricity and magnetism are not separate phenomena, but 2 faces of one unified field. In the early 20th century, the weak and electromagnetic forces were merged in what became known as the electroweak theory. The strong force joined through the principles of quantum chromodynamics, creating the standard model of particle physics, a framework that explains nearly everything except gravity. Einstein's general relativity stands apart. It tells us that gravity is not a force in the ordinary sense, but the curvature of space-time caused by mass and energy. Objects follow the straightest possible paths through this curved geometry, and what we experience as attraction is merely the shape of the world itself. This idea is breathtakingly elegant, and it has survived every test, from the bending of starlight around the sun to the detection of gravitational waves rippling through space. Yet when quantum mechanics tries to describe that same curvature, it encounters chaos. At the smallest scales, where space-time should also behave according to quantum rules, the equations explode into infinities. The quantum version of gravity, often called quantum gravity, refuses to stabilize. It is as if the smooth geometric surface of Einstein's space-time dissolves into a storm of fluctuations beyond comprehension. This failure is not merely mathematical. It suggests that our understanding of space itself might be incomplete. The familiar 3-dimensional world we inhabit could be just a shadow of a deeper structure. If gravity appears weak, perhaps it is because it is not confined to our dimensions at all. Imagine a vast ocean, and upon its surface a thin film where tiny creatures live. They can move forward, backward, and sideways, but not upward or downward. To them, the ocean seems like a flat universe. If a massive object floats above their surface, its presence might still tug upon their world, though they cannot see where that pull comes from. To those surface dwellers, that invisible influence would appear faint, mysterious, and weak. So too might our own universe be a kind of surface, a three-dimensional membrane floating in a greater, higher dimensional expanse. What we call gravity could be the faint trace of a deeper curvature spreading through those hidden dimensions. This idea may sound like science fiction, yet it has rigorous mathematical foundations. For nearly a century, physicists have explored the possibility that the universe holds more dimensions than we perceive. These are not parallel universes in the popular sense, but literal extensions of space, directions that exist orthogonal to our experience, invisible because we have no way to move through them. The first hints of this came from a German mathematician named Theodor Kaluza in the year 1921, and later from Oscar Klein in 1926. They proposed that by adding a fifth dimension to Einstein's equations, electromagnetism naturally emerges as part of geometry itself. The very force that powers magnets, light, and electricity could be explained as the curvature of a hidden spatial direction. It was a profound insight, one that hinted that all of physics might be unified through geometry. Kaluza's insight was bold. By simply extending Einstein's equations to include one extra dimension, the mathematics revealed something astonishing. The equations of motion in that hidden direction appeared identical to Maxwell's equations of electromagnetism. What we experience as electric and magnetic fields could, in principle, be geometric ripples in a fifth dimension of space. In this vision, the universe itself was not just curved, but woven in a higher dimensional pattern, and the forces we see were merely the shadows of its deeper geometry. Oscar Klein expanded on this idea a few years later. He proposed that this fifth dimension could be real yet invisible because it was compactified, curled up so tightly that it was too small for us to detect. Imagine rolling a sheet of paper into a tube. From far away, it looks like a one-dimensional line, but up close, one could see that it actually wraps around in another direction. Klein imagined the universe working in the same way. Each point in our three-dimensional space could contain a tiny looped dimension wrapped upon itself, smaller than an atom, perhaps smaller than anything measurable. At first, this idea seemed too strange to take seriously, yet it was mathematically consistent. Einstein himself was intrigued but cautious, realizing that this model hinted at something profound, that all the forces of nature might be geometric in origin. Space could be the ultimate source of everything, not a passive stage where events unfold, but the very fabric that gives rise to matter, energy, and force. However, as physics advanced through the mid-20th century, quantum mechanics grew dominant. The quantum world required a framework based on probabilities, fields, and discrete particles, not smooth geometry. Kaluza and Klein's elegant theory faded into the background, viewed as a beautiful curiosity that did not match experimental reality. Yet their idea refused to die. It lingered in the equations, waiting for the next generation of theorists to rediscover it. When string theory appeared decades later, it did not begin with the goal of explaining gravity's weakness. It began as a mathematical framework to reconcile quantum mechanics and relativity. In string theory, the smallest constituents of reality are not point-like particles, but tiny vibrating strings. The patterns of their vibrations correspond to the particles we observe: electrons, quarks, photons, and even the graviton, the theoretical quantum of gravity. But for these equations to make sense, they required extra dimensions, not 4, but 10 or 11. Suddenly, the ghost of Kaluza and Klein's idea returned with new power. If the fabric of reality truly possesses more than 3 spatial dimensions, then gravity's weakness might be no coincidence at all. In such a universe, gravity could spread through the entire multidimensional bulk, while the other forces remain confined to our familiar 3-dimensional world. The more dimensions gravity can occupy, the more diluted its effect becomes in any single one. The same way light fades as it radiates outward from a lamp, gravity would appear weak in our space because its strength is distributed across dimensions we cannot see. This concept could elegantly solve the hierarchy problem. Instead of inventing new particles or adjusting constants, it invites us to expand our vision of space itself. The question then transforms. Gravity is not weak, it is simply vast. Its influence extends beyond our limited field of perception, diffused into higher dimensions, like a mist spreading through invisible corridors of space. If true, this would mean that every step we take, every orbit, every fall is part of a larger geometry that transcends our senses. When we drop an apple and watch it fall, we are not witnessing a pull from below, but the curvature of an unseen architecture above and beyond us. Gravity, in this picture, is not a force at all, but a shadow cast from a higher dimensional structure onto our world. The idea is as humbling as it is thrilling. Our universe, with all its stars, galaxies, and living beings, might be a mere surface, a thin membrane suspended within an unfathomably larger reality. What we call the cosmos could be just one slice of a grander dimensional landscape, and gravity the only thread connecting us to it. As the 20th century closed, new generations of physicists began to test these ideas, not with imagination alone, but with experiment. They looked for signs that gravity might deviate from Newton's law at tiny distances, or that high-energy collisions might produce subtle imprints of hidden dimensions. But before we follow them into that search, we must first understand what it means to go beyond the familiar 3 dimensions of space. What does it truly mean for a universe to have a 5th dimension, or more? To answer that question, we must leave behind the comfort of visible geometry and enter a world where mathematics replaces sight, and where the true nature of space may be far stranger than our senses can ever grasp. And so the journey continues, from the weakness of gravity to the invisible architecture that may hold the secret to its power. We live our entire lives inside 3 dimensions of space and 1 of time. Forward and backward, left and right, up and down. Everything we can see, touch, or imagine exists within these directions. Time flows alongside them, giving change and motion meaning. Together, they form the 4-dimensional fabric that Einstein called space-time, a stage so vast and smooth that it holds every atom, every star, every galaxy. Yet this familiar arena may not be the whole story. It could be only a projection of a higher dimensional truth. Our senses, evolved to navigate the surface of a single planet, have never needed to perceive more than 3 spatial dimensions. We can picture a cube, a sphere, or even a curved surface, but our imagination falters beyond that. A 4th spatial dimension cannot be drawn or walked through, only described mathematically. Still, mathematics allows us to go where our senses cannot. Physicists define dimensions as independent directions in which movement or measurement can occur. In 1 dimension, motion is restricted to a single line, forward or backward. In 2 dimensions, one can move left or right and up or down, as a creature might across a sheet of paper. 3 dimensions add depth, giving our world its solid volume. But mathematics places no limit on how many such directions can exist. A 4th, 5th, or 10th dimension can be added in equations just as easily as a 3rd, even if those dimensions remain invisible to us. To understand higher dimensions, we can begin with analogies. Imagine a 2-dimensional world, a flat surface inhabited by beings who can move only in length and width but have no concept of height. To them, their universe would appear complete. If a 3-dimensional object like a sphere passed through their plane, they would see only a series of changing circles appearing and disappearing as the sphere intersected their world. They would never perceive the full shape because it extends beyond their realm of experience. In the same way, if our 3-dimensional universe were embedded within a higher dimensional space, we would see only its cross-sections. The full structure would remain hidden, detectable only through subtle effects, such as the behavior of gravity or the geometry of light. The very laws of physics could be whispers from dimensions just beyond reach. This was the profound insight that began to unfold in the early 20th century. After Einstein showed that gravity could be understood as the curvature of space-time, mathematicians began to ask, whether other forces might also be geometric. Perhaps all of physics was written in the language of geometry, each force corresponding to a different aspect of how space could twist and fold. In the year 1921, Theodore Kaluza extended Einstein's equations by proposing an additional spatial dimension. To his astonishment, the mathematics produced not only gravity, but also electromagnetism, the force responsible for light, magnetism, and electricity. By treating the universe as five-dimensional, he found that one could unify two of nature's fundamental interactions through pure geometry. Oscar Klein later suggested why this fifth dimension remained unseen. He proposed that it was compactified, curled up into a tiny circle at every point in space, so small that even the most powerful microscope could not reveal it. In this picture, the universe has both large, extended dimensions that we can move through and tiny hidden ones that exist only in theory. These compact dimensions would be smaller than an atomic nucleus, perhaps on the scale of the Planck length, about 10 to the power of -35 meters, a distance so small that it defies imagination. If Kaluza and Klein were correct, electromagnetism itself could be a manifestation of geometry in this compact dimension. Electric charge would correspond to motion around the tiny circular direction, while magnetic fields would arise from the geometry of how that dimension twists through space. The very light that shines from stars could be the ripple of a hidden dimension we cannot see. It was a revolutionary idea, uniting gravity and electromagnetism under a single geometric framework. Yet as elegant as it was, the theory struggled to fit the rest of physics. The strong and weak nuclear forces were unknown when Kaluza and Klein worked, and later discoveries would show that their model could not account for these interactions. Still, their vision planted a seed that perhaps all forces are different expressions of geometry in higher dimensions. As the decades passed, the notion of extra dimensions moved from speculation to rigorous theory. Modern physics began to see them not as fantasy, but as mathematical necessity. Whenever scientists tried to combine quantum mechanics and general relativity, the equations seemed to demand more than 4 dimensions to remain consistent. It was as if the universe itself was whispering that reality is deeper than what we perceive. If we could step outside our 3-dimensional cage, we might see our world as a vast surface floating in a higher dimensional expanse. Our stars, our galaxies, even the dark void between them, might be part of a single sheet, one layer among many, gently curved through unseen directions. In such a vision, gravity's mystery begins to make sense. If gravitational energy can spread through extra dimensions, while the other forces remain confined to our visible world, then gravity would appear weaker here simply because it is shared with realms we cannot enter. The geometry of higher space could dilute its strength, explaining the vast hierarchy between it and the other forces. To grasp this fully, we must venture into the next great leap of theoretical physics, a framework where extra dimensions are not optional curiosities, but essential building blocks of the universe itself. That leap came with the rise of string theory, where the idea of additional dimensions became not only possible, but unavoidable. The rise of string theory transformed how scientists viewed the universe. It began as a mathematical curiosity, an attempt to describe the strong nuclear force, but soon revealed something astonishing. Its equations naturally included gravity. Unlike the standard model of particle physics, which required gravity to be added awkwardly, string theory produced it on its own. It predicted a particle with no mass and 2 units of spin, exactly what a graviton should be if it exists. But there was a price for this elegance. The theory worked only if the universe had more than 4 dimensions. For the mathematics to remain consistent and free of contradictions, space had to include at least 9 spatial dimensions, plus 1 of time. Later refinements in a broader framework known as M-theory suggested an even grander structure requiring 11 total dimensions. At first glance, this seems impossible. Where are these other dimensions? Why can we not see or touch them? The answer lies in scale. these hidden dimensions could be compactified, curled up so tightly that they exist only at lengths near the Planck scale, roughly 10 to the power of minus 35 meters. To put that in perspective, an atom is about 10 to the power of minus 10 meters across. Between the size of an atom and the Planck scale lies a gap of 25 orders of magnitude, a chasm so vast that even our most powerful instruments are blind to it. Within string theory, these extra dimensions are not empty. They are folded into intricate geometric forms called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtang Yau, who describe the complex ways such shapes can fold without breaking the delicate balance of the equations. Every vibration of a string depends on the geometry of these hidden spaces. The mass, charge, and properties of every particle in our universe may arise from the way strings vibrate within those compact dimensions. Imagine plucking a guitar string. The sound it makes depends on its length, tension, and the shape of the instrument's body. In the same way, the fundamental particles of our universe are like notes produced by vibrating strings, their characteristics determined by the shape of the multidimensional space that surrounds them. If we could somehow look into the tiny Calabi-Yau structures where these vibrations occur, we might see an entire hidden symphony of geometry creating the music of matter and light. Gravity, however, behaves differently from the other forces in this picture. The electromagnetic, weak, and strong forces are confined to the surface of our visible dimensions, like ripples that travel only along a pond's surface. Gravity, by contrast, is allowed to move through all dimensions, both the ones we see and the hidden ones that surround them. This ability to leak into the higher dimensional bulk could explain its apparent weakness. Most of gravity's strength is spread beyond our reach, dispersed through invisible corridors of the larger universe. This realization turned a long-standing puzzle into a potential key to unification. If gravity's weakness arises from its multidimensional nature, then what we call space-time may be only part of a deeper structure, a kind of membrane or brain within a greater dimensional bulk. The universe itself could be a three-dimensional brain floating inside an 11-dimensional space. Such an idea changes everything. What we think of as the cosmos, galaxies, stars, planets, and the faint cosmic background that fills the void, could exist on this brain, while gravity flows freely beyond it. The higher dimensional bulk might contain other brains as well, each one a separate universe with its own version of physics, its own stars and histories. And although these worlds might be separated by distances far smaller than an atom, they would remain invisible because light and matter cannot cross between them. Only gravity could. In this picture, the mystery of gravity's weakness becomes not an accident, but a necessity. It is weak here because it is strong elsewhere, its energy shared across hidden dimensions. What seems like a feeble force in our world could be a roaring tide in the unseen bulk, echoing between membranes of reality. To explore this further, physicists began to construct models where our universe is treated as a brain. Among the most influential are those developed by Lisa Randall and Raman Sundram in the late 1990s. Their work offered a concrete mechanism to explain why gravity appears so weak compared with the other forces. By imagining an additional spatial dimension that is not simply compact but warped, they showed that gravity could be concentrated in one region of the bulk and exponentially weakened on our brain. The mathematics behind this warping are elegant. The geometry of the extra dimension curves space in such a way that gravitational energy diminishes as it moves away from a central region. To us, trapped on one side of this warped dimension, gravity seems faint. Yet in the higher dimensional picture, it remains perfectly strong. The Randall-Sundram models brought the notion of extra dimensions from mathematical speculation into a testable framework. They suggested that our universe might be only one of two brains, separated by a small gap within a 5-dimensional space-time. Gravity leaks between them, but light and matter remain confined to their respective worlds. This created a new way to think about the hierarchy problem. not as a flaw in our equations, but as a reflection of the shape of the cosmos itself. If these ideas are correct, then every gravitational interaction, every falling apple, every orbiting moon, every merging black hole, carries within it a whisper of the higher dimensions. Gravity is not merely a curvature within space-time, but a bridge, connecting our world to the bulk beyond. Yet such ideas demand evidence. Theory alone, no matter how beautiful, must face experiment. Scientists began to design tests to search for any sign that gravity behaves differently at extremely small distances, deviations that might reveal its hidden paths into extra dimensions. Others looked to high-energy collisions in particle accelerators, hoping to catch gravity in the act of escaping into the bulk. To follow those investigations, we must look at how the universe itself can become a laboratory, a stage where gravity's secrets might finally be exposed. When scientists first heard that the universe might hold more than 4 dimensions, the idea seemed too wild to test. But physics has a way of turning imagination into measurable reality. Over time, theories once thought speculative have become the foundation of new discoveries. The notion of hidden dimensions has now reached that threshold. It no longer belongs to philosophy, but to the mathematics of modern physics and the precision of modern experiment. In this view, extra dimensions are not vast open spaces like new continents waiting to be discovered. They are compact, folded, and woven into every point of space around us. Just as a tightly rolled sheet might appear flat from far away, the universe's additional directions could be wrapped up so small that we cannot perceive them. Yet their presence may shape the laws of physics in ways we can measure. One of the earliest consequences of higher dimensional theories is the prediction of Kaluza-Klein particles, echoes of motion through the compact dimension. If an electron could move in a tiny circular direction beyond the 3 we know, its motion would appear as additional energy states, like harmonics of a vibrating string. Each state would behave as a new kind of particle, heavier than the original. Detecting such Kaluza-Klein excitations would provide direct evidence of extra dimensions, though the energies required to reveal them may lie beyond the reach of our current technology. Nonetheless, their theoretical existence reshaped physics. It suggested that every known particle might have unseen partners whose properties depend on the geometry of higher space. The entire fabric of reality, from quarks to light, could be the result of motion through these hidden loops. But beyond this elegant structure lies something even more profound. The geometry of higher dimensions does not merely determine the types of particles that exist. It also dictates how the fundamental forces behave. The shape of space itself becomes the ultimate architect of reality. The curvature, the twists, and the folds of these compact spaces could explain why gravity, electromagnetism, and the nuclear forces differ in strength. Einstein's great insight, that gravity is geometry, expands naturally in this setting. If gravity is the curvature of 4-dimensional spacetime, then the other forces might correspond to curvature within the additional dimensions. Every interaction in nature could be a manifestation of geometry at different levels of the dimensional hierarchy. In such a universe, physics becomes the study of shape, and every equation a map of the unseen landscape upon which reality is built. This idea, once abstract, began to take physical meaning through the work of string theorists. They realized that higher dimensions are not optional decorations to make equations elegant. They are essential. The strings that form the basis of all matter can vibrate consistently only in spaces with specific numbers of dimensions. Remove those dimensions, and the mathematics collapses. The richness of string theory comes from the interplay between the vibrations of strings and the geometry of the hidden dimensions. Just as a violin's tone changes when its body is carved differently, the properties of particles depend on the way space itself is folded at scales too small to see. Every Calabi-Yau manifold produces a different set of possible universes, each with unique constants and physical laws. Within this vast landscape of possible geometries, our own universe may be just one melody among countless others. The presence of extra dimensions also opens a gateway to the concept of parallel branes, multidimensional surfaces floating in the higher dimensional bulk. If our universe is one such brane, others may exist nearby, each invisible to the next, except through the faint tug of gravity leaking between them. In this picture, gravity becomes not a simple field, but a messenger connecting separate realms of existence through the higher dimensional geometry they share. This vision redefines what it means to exist within the cosmos. Space is no longer a flat stage, but a living structure, intricate and layered, where unseen dimensions give birth to the visible universe. It suggests that we are not isolated in three-dimensional space, but part of a deeper continuum that extends beyond perception. When we look at the night sky, we see only the surface of that greater reality. The stars and galaxies we observe might be the luminous embroidery on a far richer tapestry, woven from dimensions we will never walk through, but can still understand through the language of mathematics. For the first time, physicists began to glimpse how the weakness of gravity, the unification of forces, and the existence of other worlds could all be facets of the same truth. That our universe is geometric in more ways than our eyes can see. And so, the path forward leads to a theory that does not merely imagine higher dimensions, but demands them. A theory where every particle, every field, and every force is the vibration of a tiny string resonating through a 10 or 11-dimensional cosmos. The next step in this journey takes us into those hidden realms of string theory, where gravity, geometry, and the very definition of reality merge into one. In the late 20th century, physics faced a crisis that was also an opportunity. The Standard Model explained nearly everything we could measure, from the behavior of quarks to the light of distant stars, yet gravity remained beyond its reach. Einstein's smooth geometry could not fit inside the quantum cage. When physicists tried to describe gravity as a particle exchange, the mathematics broke apart into infinities that refused to cancel. Space and time themselves seemed to dissolve into chaos at the smallest scales. Out of this turmoil emerged a strange new idea, that the universe is not made of point-like particles at all, but of tiny one-dimensional strings. Each string vibrates like the filament of a cosmic instrument, its different modes of vibration giving rise to the variety of particles and forces we see. The beauty of this idea lay in its simplicity. A single type of object, vibrating in countless ways, could produce the entire orchestra of physics. But simplicity in concept does not mean simplicity in mathematics. To make sense, the theory required a very specific stage. When physicists wrote down the equations that govern string vibrations, they found that the mathematics only worked if the universe contained more dimensions than 4. The minimum number was 10. Later, when different versions of the theory were unified under a broader framework called M-theory, that number grew to 11. This revelation was astonishing. It suggested that our familiar world, the entire cosmos of galaxies and light, was only a small slice of a far greater dimensional structure. The extra dimensions were not vast open spaces, but hidden, curled up at scales unimaginably small. The geometry of those compact dimensions determines the vibrations of strings, and therefore the fundamental nature of matter and energy. To visualize this, imagine each point in ordinary space as a tiny bundle of additional directions, curled upon themselves in intricate shapes. These shapes are known as Calabi-Yau manifolds, named after the mathematicians who discovered them. They are not simple loops or spheres, but complex, multidimensional surfaces folded with exquisite precision. Within these folds, the strings vibrate, and the patterns of those vibrations create everything: electrons, photons, quarks, and even the force of gravity itself. The geometry of a Calabi-Yau manifold acts like the body of a musical instrument. The same string, when placed in a differently shaped space, will produce a different tone. Likewise, the properties of particles, their masses, charges, and interaction strengths depend on how the hidden dimensions are shaped. Change the geometry, and you change the physics. In this sense, our universe is a specific melody played upon the instrument of higher dimensional space. Gravity stands apart in this cosmic symphony. In string theory, the graviton, the quantum particle of gravity, arises naturally as one of the vibrational modes of a closed string, a loop with no endpoints. Because it is closed, it is not confined to any surface or brane. It can move freely through all dimensions. By contrast, the other forces come from open strings, whose ends are anchored to the brane that represents our universe. These open strings cannot leave the brane, which is why electromagnetism, the weak force, and the strong force remain trapped in our familiar four-dimensional world. This simple difference, open versus closed, could explain one of the oldest mysteries in science. If gravity alone can travel into the higher dimensional bulk while the other forces cannot, then it will appear weaker in our universe because its influence is spread across a larger volume of space. What we perceive as the feeblest of forces might actually be the most far-reaching, whispering across dimensions that light and matter will never touch. The mathematics supports this vision elegantly. When scientists calculate how gravitational field lines behave in such a multidimensional space, they find that the apparent weakness of gravity in 3 dimensions follows naturally. The force does not vanish, it only thins as it radiates into directions we cannot see. The geometry of those hidden paths dilutes its intensity, just as the brightness of a lamp fades as its light spreads through a room. If true, this interpretation would transform our understanding of reality. It would mean that what we experience as space is not the entire fabric of the universe, but only a visible layer, a surface within a grander dimensional realm. The true geometry of existence may be far more complex, a vast web of interwoven dimensions, each contributing to the physical laws we observe. This notion reshapes even the concept of a point in space. A point, in the language of string theory, is not truly zero-dimensional. It is a vibrating loop, a small string whose oscillations encode all the information about its environment. The smallest unit of matter is therefore not an indivisible particle, but a tiny pulse of geometry. Space itself becomes an active participant in the creation of reality, not an empty void, but a dynamic medium humming with unseen vibrations. As scientists explored the mathematics further, they found that the theory was not just consistent with gravity, it required it. The existence of a spin-2 particle, the graviton, was unavoidable. In this way, string theory became the first framework in which quantum mechanics and general relativity could coexist without contradiction. It offered a glimpse of the long-sought theory of everything, a single description that unites all the forces of nature. Yet the price of this unity is high. The extra dimensions, so essential to the theory's consistency, are beyond direct observation. They influence everything but reveal nothing of themselves. We can infer their presence only through the properties of the particles and forces that emerge from them. It is as if the universe hides its foundation behind a veil, showing us only the shadows cast by its higher geometry. For those who study it, this is both a triumph and a torment. The equations sing with coherence, but the melody remains unheard by experiment. The challenge, then, is to find a way to test the existence of these hidden realms, to see whether gravity's faint voice truly echoes from dimensions beyond. The beauty of string theory lies in how it turns the universe into a conversation between geometry and vibration. Every atom, every photon, and every flicker of gravity becomes a note in a vast multi-dimensional composition. The hidden dimensions, those curled and folded Calabi-Yau spaces, are the resonant chambers of that composition. They determine the harmony of existence. To glimpse their structure, one must think not in images, but in relationships. A Calabi-Yau manifold is a shape beyond human vision, defined not by edges and corners but by symmetries and equations. Within its folds are pathways that connect and loop, spaces that twist back on themselves, creating a network of geometric resonances. Each possible shape defines a different version of physics. Some would allow stars and chemistry. Others would collapse or expand too violently for life to exist. Our universe may simply be one stable configuration among an enormous landscape of possibilities. These hidden shapes also contain the seeds of duality, one of the most profound discoveries in theoretical physics. Duality means that two very different-looking theories can describe the same underlying reality. In string theory, a universe with small, compact dimensions can behave exactly like another universe with large ones, if the relationships among their geometries are tuned in a specific way. The mathematics links opposites, showing that what seems vast might also be infinitesimal, that strength and weakness, distance and nearness can exchange roles. This realization suggests that the boundaries of reality are not absolute. The universe is self-reflective, capable of describing itself in more than one language. Even gravity, the most ancient of forces, may have a dual face in another dimension, mirrored through a principle known as ADS-CFT, a correspondence between a gravity theory in a higher dimensional space and a quantum theory on its boundary. Though this idea belongs more to advanced physics than to direct experience, it hints at something astonishing. Gravity, space, and time might be the emergent shadows of deeper quantum information encoded in those hidden dimensions. The Calabi-Yau manifolds are not static. In the mathematical sense, they can vibrate, stretch, and twist. These motions, though invisible, could leave traces in our universe. They might influence cosmic expansion, the formation of dark energy, or even the properties of gravitational waves. The vacuum of space is not truly empty. It is alive with the geometry of higher dimensions, humming beneath the silence of ordinary perception. In some versions of string theory, these hidden dimensions are not all microscopic. Some could extend far beyond our comprehension, large enough for gravity to explore, but too subtle for light or matter to reveal. This is where the concept of branes emerges. A brane, short for membrane, is a multidimensional object that can exist within the higher dimensional bulk. Our universe itself could be such a brane, a vast three-dimensional sheet embedded within a greater reality. On this brane, all familiar forces and particles are confined, bound by the ends of open strings that cannot leave. Gravity, carried by closed strings, is the only force that can travel through the bulk, reaching into dimensions beyond the brane. This means that when we feel gravity's gentle pull, we may be sensing the influence of the bulk itself, a whisper from the larger dimensional space in which our universe floats. The concept of branes connects naturally with the work of Kaluza and Klein. Their hidden circular dimension was the first step. String theory and M-theory expanded that idea into an entire architecture of multidimensional surfaces. Instead of one compact loop, there could be countless folds, each supporting its own physics. Some might contain universes parallel to ours, separated not by distance, but by dimensional orientation. These worlds would be invisible, yet their gravity could pass through the bulk and subtly affect ours. Such a vision reframes existence. The cosmos we see, stars, galaxies, and the vast cosmic web, could be a shimmering skin upon a far greater structure. The true universe might be a higher dimensional ocean, and our reality a single wave upon its surface. In this vast ocean, gravity is not merely a force, but a flow, a current moving between branes, linking realities that otherwise cannot touch. Physicists call this the Brane-World picture. It emerged from string theory as more than metaphor. Its equations describe how gravity behaves when space itself has thickness. If our universe is a brane, then the bulk around it can warp and stretch, influencing how gravity moves. The curvature of this bulk could explain why gravity's strength appears to fade as it crosses dimensions. Among the most elegant realizations of this idea came from the work of Lisa Randall and Raman Sundram. They proposed that our universe might lie in a five-dimensional space-time, where the fifth dimension is not flat, but warped like a valley. The geometry of this warp naturally explains the hierarchy between gravity and the other forces. On one brane, gravity is strong. On ours, it appears weak because the warp spreads its influence thinly. This is not an illusion, but a geometric truth, a shadow cast by curvature in the higher dimensional bulk. If their model is correct, then gravity's faintness is not a defect, but a design. It is the signature of higher dimensional geometry. The force that shapes planets and stars is not limited by our space, but shared with others. What we feel as the weakest force in nature could be the most fundamental link between all dimensions. In this light, the weakness of gravity becomes a message. It tells us that our world is not isolated. It tells us that beyond the veil of three-dimensional perception lies a grander, folded cosmos whose geometry gives birth to everything. And so, as the mathematics of string theory deepened, a new picture of the universe began to form, a picture where every particle, every field, and every curvature of space-time is the surface expression of something deeper in the bulk. The next step in this journey will take us there, into the Brane-World itself, the vast higher dimensional sea where gravity roams freely and our universe floats as a fragile membrane within the whole. Imagine space not as emptiness, but as a surface, a vast flexible sheet drifting through a higher dimensional ocean. Every star, every planet, and every photon of light lies upon this surface, unable to leave it. This is our universe, a three-dimensional membrane, or brane, floating within a greater multidimensional space known as the bulk. The idea sounds poetic, yet it arises directly from the mathematics of string theory and M theory, where branes are as real as the strings themselves. In this vision, our familiar world is confined to the brain. The atoms that make up our bodies, the electromagnetic fields that illuminate the sky, the nuclear forces that hold matter together. All are vibrations of open strings whose ends are attached to the brain. These strings cannot detach. They are bound by the geometry of higher dimensions. But gravity, carried by closed loops of string, is different. It can move freely through all dimensions, wandering beyond the brain into the bulk. That freedom explains everything. Gravity feels weak, not because it is small, but because most of it escapes our universe. Its field lines spread into the higher dimensional space, leaving only a diluted remnant for us to measure. The Brane-World concept changes how we think about the cosmos. Instead of existing inside space, we are part of its surface. The universe becomes a living membrane, flexing and rippling within the bulk. When a planet moves, when a star collapses, or when a black hole merges, those motions send gravitational ripples not only through our space, but also into the higher dimensional ocean beyond. Some of those waves may return, echoing faintly back upon us, while others vanish into the bulk forever. To understand how this works, imagine a drumhead vibrating in air. The drum's surface is two-dimensional, yet its sound waves spread into three dimensions. The air carries energy away, allowing the drum's vibrations to fade more quickly than they would if trapped in silence. In much the same way, our universe loses gravitational energy to the bulk. Gravity's weakness, therefore, is not a flaw in its nature, but a consequence of this cosmic leakage. In the late 1990s, physicists Lisa Randall and Raman Sundram brought precision to this poetic image. They proposed two related models of the universe, now known as Randall-Sundram 1 and Randall-Sundram 2. Both envision our universe as a brane embedded in a five-dimensional space-time. The key difference lies in how that fifth dimension behaves. In the first model, the bulk contains two branes, separated by a finite gap, with the geometry between them warped exponentially. In the second model, there is only one brane, but the extra dimension extends infinitely, its curvature shaping how gravity diminishes. The equations of these models showed something astonishing. The warping of the extra dimension could naturally explain the hierarchy problem. The immense difference between the strength of gravity and the other fundamental forces. Instead of being arbitrary, this hierarchy emerges from the geometry of space-time itself. In the Randall-Sundrum picture, the curvature of the fifth dimension focuses gravity toward one brane and weakens it on another. If we inhabit the weaker brane, the gravitational force we feel will appear tiny, even though it remains powerful in the higher dimensional bulk. The mathematics of this warping is subtle, yet beautiful. The curvature acts like a gravitational lens, concentrating field lines in certain regions and stretching them in others. In ordinary space, Newton's inverse square law describes how gravity weakens with distance. But in a warped higher dimensional space, this simple law is modified. The strength of gravity depends not only on distance, but on how the extra dimension bends around the brane. In this way, geometry sculpts force. The implications reach far beyond theory. If our universe truly floats as a membrane within a five-dimensional bulk, then other branes may exist parallel to ours. They could lie separated by minuscule distances, far smaller than an atom, yet remain completely invisible because light and matter cannot travel between them. These neighboring branes might host their own stars, galaxies, and even forms of life, unaware of our existence. Gravity, however, could bridge the gap. It might leak from one brane to another, allowing the universes to influence each other faintly through the bulk. Such a possibility redefines the very meaning of a universe. What we call the universe could be only one layer in a grand multidimensional stack, each brane a separate reality drifting through the higher dimensional ocean. The bulk itself would be the true cosmos, a vast and silent space connecting all these membranes through the invisible flow of gravity. This idea also gives new meaning to cosmic expansion. If the bulk is curved, the motion of our brane through it could appear as the accelerating expansion of space. What we attribute to dark energy might in part be a geometric effect, the motion of our membrane within the bulk's warped geometry. The fabric of the cosmos could be stretching not because of some mysterious energy, but because we are moving through a higher dimensional landscape. The Brane-World picture has even deeper consequences for the nature of black holes. In classical general relativity, a black hole curves space-time so intensely that not even light can escape. In a higher dimensional bulk, the curvature could extend beyond the brane, creating what physicists call a black string or black brane, a gravitational object whose horizon stretches through multiple dimensions. To an observer on our brane, such a structure would look like an ordinary black hole, but in the bulk it would be an elongated, multi-dimensional funnel connecting different layers of reality. If such objects exist, their gravitational signatures could reveal the fingerprints of the bulk. The way they merge, emit waves, or evaporate might deviate slightly from Einstein's predictions. Detecting those deviations would be one of the most direct ways to prove that extra dimensions are real. In this sense, the Brane-World universe is not merely a metaphor, but a framework that invites observation. It gives specific predictions, small but measurable, that modern instruments can test. The strength of gravity at short distances, the behavior of gravitational waves, and even the pattern of cosmic expansion all become windows into the bulk. To follow this trail, physicists have turned their attention to experiments, delicate measurements designed to test whether gravity truly obeys the inverse square law down to the smallest accessible scales. If the force deviates even slightly from Newton's rule, it could be the first whisper of higher dimensions calling through the veil. The idea that gravity might leak into unseen dimensions sounds audacious, but science thrives on audacity, tempered by precision. If higher dimensions exist, they must leave traces, faint but measurable distortions in the way gravity behaves. The challenge is to find them. Physicists began by testing Newton's law of gravitation at the smallest possible scales. According to classical physics, the strength of gravity between two masses decreases with the square of the distance between them. Double the distance, and the force drops to 1/4. This law has been confirmed for planets, moons, and even laboratory objects. But if extra dimensions are real, that law could break down at very small separations. The reason lies in geometry. In 3 dimensions, gravitational field lines spread across a spherical surface, but if more dimensions exist, those lines would have extra directions to expand into, making the force fall off faster than the inverse square. In the late 20th and early 21st century, a team at the University of Washington, known as the EOT WASH Group, built one of the most sensitive experiments in the world to test this possibility. They suspended metal discs, drilled with intricate holes, and measured the minute torques caused by gravity acting between them at separations smaller than a millimeter. Their goal was to see whether Newton's law remained exact, or whether some hidden influence slightly altered it. The measurements required exquisite precision. Even the gravitational pull of a nearby person, the vibration of the building, or the presence of air currents could corrupt the data. The scientists worked in vacuum chambers, shielding their apparatus from every known disturbance. The results were remarkable. Down to distances of about 1/10 of a millimeter, Newton's law held true. No deviation appeared. Yet this absence of deviation did not close the door on higher dimensions. It only set limits. If extra dimensions exist, they must be smaller than the smallest scale yet probed. The experiment sharpened the mystery, narrowing the possible size of the hidden world, but not eliminating it. Other scientists sought evidence in a different arena, the colossal energies of particle collisions. At the Large Hadron Collider in Geneva, protons are accelerated to near the speed of light and smashed together with enough energy to recreate conditions moments after the Big Bang. If gravity can move into extra dimensions, then in these collisions, some of that gravitational energy might escape into the bulk. To us, it would appear as missing energy, a gap in the balance of momentum that no known particle could account for. Detecting such an imbalance would be like catching gravity in the act of leaving our brain. Physicists have searched through mountains of collision data for such events. So far, none have been confirmed, but each new round of experiments extends the limits. The absence of detection does not mean failure. It means refinement. The boundaries of what is possible grow narrower, the equations more precise. If gravity leaks, it does so delicately, a whisper, not a shout. Meanwhile, cosmologists turned their attention to the heavens. The early universe was a furnace of energy and motion, where gravitational interactions were intense enough to leave imprints that might still be visible. If extra dimensions shaped those primordial moments, their influence could appear in the cosmic microwave background, the afterglow of the Big Bang. Tiny variations in its temperature and polarization might contain the fingerprints of higher dimensional effects. Satellites like Planck and WMAP have mapped that ancient light with extraordinary detail, searching for patterns that cannot be explained by ordinary physics alone. Some subtle anomalies exist, but they remain ambiguous. The cosmos does not give up its secrets easily. Then came another kind of observation: gravitational waves. When massive objects such as black holes or neutron stars collide, they send ripples through space-time itself. These waves travel vast distances, carrying information about their origins and about the medium they pass through. If our universe is a brane, some of those waves might escape into the bulk or reflect from it, changing the signal we detect. The Laser Interferometer. Gravitational Wave Observatory, known as LIGO, began detecting such events in the year 2015. Each detection confirmed Einstein's predictions with stunning accuracy, yet also provided a new opportunity to look for deviations that might hint at extra dimensions. So far, the data align perfectly with four-dimensional physics. But the precision of these measurements continues to improve. If even a fraction of a percent of gravitational energy disappears into the bulk, future detectors might reveal it. Scientists have proposed building larger and more sensitive instruments, both on Earth and in space, to listen for echoes, faint resonances that could return from the higher dimensional ocean surrounding our brain. The search does not end there. Some researchers speculate that the mysterious phenomena we call dark matter and dark energy could be signs of higher dimensional gravity. Dark matter reveals itself only through its gravitational pull, as if invisible mass were scattered throughout the cosmos. Dark energy drives the acceleration of cosmic expansion, a pressure with no known origin. Both could, in principle, arise from the influence of nearby branes or the curvature of the bulk itself. In this way, the Brane-World model links our most profound mysteries into a single picture. Gravity's weakness, dark matter's invisibility, and the universe's accelerating expansion may all stem from the same source: the geometry of higher dimensional space. What we observe as separate puzzles might be the projections of one deeper truth. The search for that truth continues through experiment and observation. Every new measurement of gravity, every detection of a gravitational wave, every study of cosmic expansion brings us closer to knowing whether we truly inhabit a membrane within a greater bulk. If the evidence is found, it will redefine the meaning of reality. The sky we see at night will no longer be the boundary of the universe, but a window into something vaster, a realm where other branes drift beside ours, each carrying its own version of existence. The Brane-World vision challenges everything we once believed about space, time, and isolation. If our universe truly floats within a higher dimensional bulk, then the cosmos we observe may be only a thin membrane in a grander structure that stretches beyond imagination. The familiar idea of an enclosed universe gives way to something far more intricate, a web of parallel realities linked through the faintest thread of gravity. Gravity becomes the diplomat between worlds. It travels where light cannot, seeping through the bulk, brushing against other branes that may lie near ours in dimensional space. Most of its energy never returns, but some part of it might drift back as echoes, faint ripples that carry the signature of those hidden realms. This image transforms the weakness of gravity into a revelation. What we call weakness is simply the cost of sharing. In such a universe, every black hole, every star, and every orbiting planet becomes a gateway for gravity's journey into the higher dimensional ocean. When two black holes merge, the gravitational waves that escape may not all remain within our brain. Some could leak outward, their energy dissipating into the bulk, altering the pattern that reaches our detectors. Even a small fraction lost to higher dimensions could change the shape of the wave. If future observatories detect such anomalies, they may reveal not only the existence of extra dimensions, but also their curvature and scale. The structure of a black hole itself may differ in a Brane-World cosmos. In four-dimensional general relativity, a black hole is fully described by its mass, spin, and electric charge. But in higher dimensions, the horizon can stretch and distort, forming elongated objects known as black strings or black branes. These higher dimensional structures could extend through the bulk, connecting different branes or folding back upon themselves. Their gravitational fields would look ordinary from within our universe, but would conceal complex shapes in the unseen dimensions beyond. Some physicists have explored whether such higher dimensional black holes could shed light on one of the greatest puzzles in physics, the information paradox. In ordinary black holes, information about matter that falls in appears to vanish, conflicting with quantum mechanics. But if a black hole extends into the bulk, the missing information might not be lost at all. It could escape into the higher dimensional region, encoded in ways our four-dimensional physics cannot describe. What seems like disappearance could merely be translation, data slipping into another layer of reality. The same reasoning applies to the birth of the universe itself. In some cosmological models, the Big Bang may not have been an explosion from a singular point, but a collision between branes drifting in the bulk. When two such membranes approached and met, the immense energy of their impact could have created the hot, dense state that we now see as the beginning of time. The echoes of that collision might still reverberate through cosmic background radiation or through the large-scale structure of galaxies. If such evidence is ever found, it would mean that our universe is not a singular event, but part of an eternal ballet of branes, colliding, rebounding, and creating new worlds across the higher dimensional expanse. The implications of this vision stretch beyond physics into philosophy. The Brane-World model suggests that our universe is not the center of reality, but one of many layers in a greater dimensional whole. The boundaries between universes are not absolute, they are geometric. What separates us from other worlds is not distance, but dimensional orientation, a twist in the structure of space itself. Even the concept of nothingness changes. The bulk, though seemingly empty, is filled with the geometry of higher dimensions. Its curvature gives rise to the forces we experience. Its hidden symmetries determine the constants of nature. The vacuum of space becomes a living entity, the stage and the script of existence intertwined. This realization carries a certain humility. It reminds us that the laws we take as universal may be local expressions of a deeper, multidimensional reality. The constants that shape chemistry and biology could be consequences of how our brain is curved within the bulk. Change the curvature, and an entirely different universe could emerge, governed by different mathematics, different particles, and perhaps different notions of time. And yet, despite its vastness, this higher dimensional cosmos may still be connected by gravity's gentle thread. That thread links all brains, all realities, and all events. It weaves the entire bulk into a single, coherent tapestry. The Brane-World idea also reshapes our understanding of cosmic destiny. If gravity can leak into the bulk, energy might slowly drain from our universe over eons, altering the long-term expansion of space. The faint hum of gravity could carry pieces of our cosmos away, distributing them across the higher dimensional ocean. The end of our universe might not be a cold silence, but a diffusion, a slow blending into the bulk from which new brains may eventually emerge. Such possibilities are breathtaking, yet they rest on firm mathematical ground. They arise from the same equations that describe string vibrations and higher dimensional geometry. They show that the weakness of gravity is not a flaw, but a clue, a window through which we can glimpse the architecture of reality itself. Every observation we make of gravity, every experiment that tests its laws, is therefore a dialogue with the higher dimensions. We may not see the bulk directly, but we feel its presence in every orbit, every fall, every curvature of space-time. The next chapter in this journey turns to that dialogue itself, the flow of gravity between dimensions. If gravity can escape into the bulk, could it also return? Could we feel its echo as an unseen force, subtle yet powerful, shaping the cosmos in ways we have only begun to imagine? To answer these questions, we must follow the path of gravity beyond the edge of our universe and explore what happens when it crosses the dimensional boundary. There, in the invisible space between brains, lies the key to understanding why the universe holds together at all. Imagine a two-dimensional world, a universe drawn across a single sheet of paper. Its inhabitants can move forward, backward, left, and right, but never upward. They know nothing of the third dimension, yet the third dimension surrounds them completely. If you were to press your fingertip above their surface, they would see only the outline of a circle, not the full shape. To them, your finger would appear as a mysterious object whose presence changes the curvature of their world. Now imagine that same fingertip drawing near a heavy object resting upon their sheet. The two-dimensional beings might feel a force pulling them toward it, yet they would never understand that what they call gravity is actually the result of curvature caused by something above them, something they cannot see. This simple analogy captures the essence of the gravity leak hypothesis. Just as the creatures of the sheet experience the shadow of a three-dimensional event, we may be feeling the diluted trace of gravity leaking from a higher dimension. What we call weakness is the symptom of its vastness. Physicists use this idea to reimagine gravity as a geometric echo. Instead of existing solely within our familiar space, gravitational fields could spread throughout the higher dimensional bulk. Their lines of influence would extend outward, branching into the unseen directions. The more directions they can occupy, the thinner their strength becomes within any single one. This is the reason a magnet can lift a paperclip against the pull of an entire planet. It is not that gravity is frail, it is that gravity's energy is dispersed, shared with dimensions invisible to us. Our three-dimensional brain receives only a fraction of its full intensity. The rest flows beyond, through the corridors of the bulk. The mathematics of this spreading are elegant and merciless. In three-dimensional space, gravity weakens with the square of distance. Add one hidden dimension, and the weakening follows a cube. Add more, and the fall-off grows steeper. Every new dimension siphons strength away from the visible world. By the time gravity reaches us, it has already extended its influence across realms that light and matter can never visit. Yet this same diffusion explains why gravity is also universal. Unlike the other forces, it cannot be confined. Electromagnetism and the nuclear forces cling to the brain, bound by the ends of open strings. Gravity, carried by closed strings, drifts freely. Its weakness becomes its reach. Because it can wander through the higher dimensional bulk, it connects everything, not just within our universe, but potentially across others. In this framework, gravity's apparent fragility is an illusion born of our confinement. We are like fish at the bottom of a pond, feeling the currents of a river that runs far beyond our vision. The true river is immense, but we sense only the eddies that pass through our small domain. The equations of the Brane-World model support this view. When the gravitational field is allowed to spread into an extra dimension, the effective strength we observe within our brain matches the measured value of Newton's constant. The numbers align, not through coincidence, but through geometry. What once seemed an arbitrary weakness becomes a predictable result of higher dimensional space. This realization transforms gravity from a problem to a messenger. Its faintness is the signal of a greater reality. Every falling object, every orbiting moon, every ripple of space-time becomes a communication between dimensions. Gravity leaks outward, but it also carries information inward. The shape of our universe is written into how gravity flows through the bulk and back again. If the bulk contains other brains, other universes, then gravity could act as the thread connecting them. Each brain would generate its own gravitational field, spreading through the higher dimensional ocean. Where those fields overlap, they could interact subtly, influencing each other across the bulk. These interactions might be invisible to light, but not to gravity. The missing mass we attribute to dark matter could, in theory, be the gravitational imprint of matter residing on a neighboring brain. To explore this idea, imagine again the two-dimensional world. If a massive object floats just above their sheet, the inhabitants would feel its presence as a weak gravitational pull, though they could not see the source. They would infer an unseen mass, just as we infer dark matter from the motions of galaxies. The analogy is almost perfect. What they call a mystery is simply the shadow of a higher dimension. In our own universe, the same logic might apply. The dark matter that sculpts galaxies could be ordinary matter from another brain, its gravity leaking across the bulk and shaping ours. This would explain why dark matter interacts gravitationally but not electromagnetically, because light cannot cross the boundary between brains, while gravity can. This hypothesis, if true, would mean that our universe is not isolated, but part of a multi-dimensional ecosystem. The bulk would hum with gravitational exchanges, a silent conversation between realities. Each brain would bend the geometry of the bulk in its own way, creating an intricate web of curvature. Gravity would flow along this web, connecting worlds like filaments of a cosmic tapestry. If the Brane-World models of Randall and Sundram provided the mathematical framework, the gravity leak hypothesis provides the physical intuition. It tells us what it means to live on a brain, to feel only the weakened residue of a force that exists in full strength elsewhere. It suggests that every time we measure gravity, we are probing the boundary of the visible universe. The next step is to ask whether this flow of gravity can be detected, not indirectly, but through direct experiment. If gravity leaks out, can we ever see it leaving? Could its departure leave a measurable trace, a missing piece of energy, a distortion in the pattern of space-time, or a deviation from Newton's perfect law? These questions lead us to the edge of what modern science can measure. To test the hypothesis, we must search for the faint fingerprints of higher dimensions hidden in the smallest and largest scales of the universe. From tabletop experiments that weigh the invisible to cosmic observatories that listen for whispers in the gravitational sea, every observation becomes a clue. In the chapters that follow, we will explore those clues, the delicate tests that seek evidence of gravity's escape into the bulk and perhaps its return. For if gravity can leak outward, what prevents it from flowing back? What if the bulk itself can respond, sending waves of geometry into our brain, shaping the very structure of our cosmos? To answer that, we must look at the conversation between universes, the echoes of gravity that travel through the higher dimensional sea, and the signs they may leave upon our world. If gravity truly leaks into dimensions beyond our reach, its escape must leave traces in the world we can measure. Though faint, those traces could appear wherever gravity interacts with energy, motion, or curvature. Scientists have spent decades designing instruments sensitive enough to catch them, hunting for the smallest deviations that might reveal the presence of the higher dimensional bulk. The first approach is to study gravity at its weakest. At large scales, its pull shapes planets and galaxies, but at microscopic distances, it becomes nearly impossible to measure. If extra dimensions exist, they would begin to affect gravity's behavior at small separations, perhaps a millimeter, perhaps much smaller. The prediction is clear. Beyond a certain point, Newton's inverse square law would no longer hold perfectly. The gravitational force would fall off faster, following a curve shaped by the geometry of the hidden dimensions. Experiments like those performed by the Earphones group have tested this with astonishing precision. They suspended metal plates only a fraction of a millimeter apart and measured the tiny twist caused by gravity's pull. The sensitivity of their instruments is extraordinary, able to detect torques smaller than a trillionth of a Newton. Every vibration, every thermal fluctuation, every heartbeat of the Earth itself had to be accounted for and removed. The result was a silence so deep that only the faint whisper of gravity remained. And yet, within that silence, no deviation has been found. Gravity continues to obey Newton's law down to the smallest measured distances. To some, this absence is disappointing. To others, it is thrilling. Every null result narrows the window of possibility, telling us where the extra dimensions cannot be and how tightly they must be curled. It is as though we are pressing our ear against the cosmic wall, listening for echoes that are not yet loud enough to hear. Another way to search for leakage is through the energy balance of high-energy collisions. When protons smash together at near light speed inside the Large Hadron Collider, their energy should be conserved perfectly. Every bit of momentum that goes in must come out as measurable particles. But if gravity escapes into extra dimensions, a fraction of that energy might vanish, carried away by a graviton slipping through the bulk. In our detectors, it would appear as missing energy, a hole in the accounting of the collision. Such events would be rare and subtle, hidden among billions of ordinary interactions. Physicists sift through the data like archaeologists of motion, searching for patterns that do not belong. They have found no clear sign yet, but they have established boundaries. If gravitons do escape, the dimensions they travel through must be smaller than we once hoped, or shaped in ways that make their leakage harder to detect. Each year of data tightens the net, constraining the geometry of the bulk with greater precision. Still, the absence of proof is not the same as the proof of absence. Gravity's nature ensures that it remains elusive. Its influence grows weaker by the square of distance, and if it spreads through hidden dimensions, its measurable strength within our own brain becomes even smaller. The very thing that makes gravity a window into the bulk also makes it the most difficult phenomenon to study. But there are larger cosmic laboratories where gravity reveals itself on grander scales. The collisions of black holes and neutron stars, the warping of space-time across billions of light years, the accelerating expansion of the universe. All of these are experiments written by nature itself. In these colossal events, the energy of gravity may be strong enough to leak into the bulk in ways we can detect. Consider a pair of black holes spiraling together. As they merge, they release an enormous burst of gravitational waves, ripples in space-time that carry away a small fraction of their mass as pure energy. If gravity can escape into the bulk, then not all of that energy would remain within our universe. Some portion would leak outward, changing the shape of the signal we detect. The waves would arrive slightly weaker or slightly distorted compared to the predictions of general relativity. When LIGO detected the first gravitational waves in the year 2015, physicists immediately began comparing the data to the predictions of higher dimensional models. The observed signals matched Einstein's theory perfectly, but even that match provides information. It tells us that if gravity leaks, the process must be subtle, occurring on scales smaller than our instruments can yet resolve. Future detectors, larger, quieter, and more sensitive, may be able to measure the faint residue of gravity's escape. Some cosmologists propose that the very expansion of the universe might bear the mark of gravity's leakage. If energy slowly drains from our brain into the bulk, it could mimic the effect of dark energy, causing space to expand faster than expected. The acceleration we observe might not be driven by a mysterious force, but by the slow diffusion of gravitational energy into higher dimensions. In this view, the cosmos expands not because of some new ingredient, but because we are losing a small fraction of ourselves into the unseen. If that is true, then every galaxy, every star, and every planet is contributing drop by drop to the higher dimensional sea. Over cosmic timescales, the total loss could reshape the destiny of the universe. Perhaps it will never end in a cold stillness, but in a quiet surrender, a gradual merging with the bulk that gave birth to it. The possibility is profound. Gravity's weakness, so long regarded as an obstacle, becomes a clue. It hints that our universe is porous, that space itself is not a sealed container, but a membrane through which energy can flow. This flow may explain not only why gravity seems weak, but also why the universe evolves as it does. Physicists continue to test these ideas with increasing rigor. They design new torsion balances, build cryogenic detectors that can measure forces 1 billion times weaker than a feather's touch, and plan gravitational observatories in space that can hear the universe's faintest murmurs. Each experiment brings us closer to understanding whether gravity truly leaks, and, if it does, where it goes. But another question remains, perhaps even more mysterious. If gravity can escape, can it also return? Could disturbances in the bulk send gravitational echoes back into our world, subtle reverberations that influence the cosmos in ways we do not yet recognize? To answer that, we must follow gravity beyond our brain and explore the echoes that might drift back from the higher dimensional sea. The hidden feedback that could connect our universe with others. In every era of science, there comes a question that cannot be ignored. A question that stretches imagination beyond the reach of our instruments. For the physicists of today, that question is simple, yet staggering. If space truly hides unseen dimensions, how would we ever know? The search for extra dimensions is unlike any other pursuit in human history. It is a quest not for a new planet or a new element, but for new directions of existence itself. We are trying to detect the geometry of what cannot be seen, to measure the invisible fabric of the universe by its faintest tremors. The journey takes us into laboratories where gravity is weighed with the precision of a dream, and into accelerators where the energy of creation itself is reborn for a fleeting instant. Everything begins with gravity. It is the one force that refuses to behave. Electromagnetism, the weak force, and the strong force all fit perfectly into the equations of quantum mechanics, but gravity remains an outsider, a poet among engineers. It is far weaker than it should be, a trillion times less powerful than the electromagnetic force. If the universe were truly four-dimensional, this imbalance would be incomprehensible. Yet if gravity leaks into hidden dimensions, the weakness suddenly makes sense. It would not be weak, merely diluted, its strength spread through unseen directions. So how can we test that idea? The first and most direct approach is to measure gravity at the smallest possible scales. Newton's inverse square law tells us that the gravitational attraction between two objects should decrease in proportion to the square of the distance between them. If extra dimensions exist, that rule should eventually break. At distances smaller than the size of those hidden dimensions, gravity would start to spread into them, weakening faster than predicted. In the laboratories of the Earphones group at the University of Washington, physicists have built experiments so delicate they can hear gravity whisper. They suspend thin disks of metal, one above another, separated by distances smaller than the width of a human hair. The upper disk is attached to a torsion fiber so fine it can twist under a torque of less than a trillionth of a newton. As the lower disk rotates, the gravitational pull between the two produces an almost imperceptible twist in the fiber. To perform such an experiment requires a cathedral of stillness. Every vibration, every sound, even the beating of a human heart can drown the signal. The entire apparatus is enclosed in vacuum chambers, shielded from magnetic interference, isolated from seismic noise, and cooled to eliminate thermal drift. For days, the disks hang in darkness, and scientists watch for the tiniest shift in a laser beam reflected from a mirror glued to the fiber. When they analyze the data, the answer comes back clear. Gravity still follows the inverse square law. Down to separations of a few tens of micrometers, there is no sign of deviation. The hidden dimensions, if they exist, must be smaller than that, curled within lengths 1 billion times smaller than the thickness of paper. Yet this null result is not defeat, it is direction. It tells us that the geometry we seek hides deeper than before. Each improvement in sensitivity closes one door and opens another. The map of possible universes grows narrower, but more defined. The silence of the measurement speaks volumes about the structure of reality. Other experiments look for the signature of gravity's escape, not in stillness, but in violence. Inside the Large Hadron Collider, protons race around a 27-kilometer ring at nearly the speed of light. When they collide, the energy density momentarily reaches that of the early universe, conditions under which gravity might reveal its true form. If the world has extra dimensions, those collisions could generate gravitons, the hypothetical quanta of the gravitational field, capable of escaping into the bulk. To the detectors surrounding the collision point, the event would appear unbalanced. The total energy before and after the collision would not match. Some would vanish into the unseen. Physicists call these missing energy events. They are among the rarest and most difficult to interpret, for any imperfection in the detector can mimic the effect. Yet teams of scientists sift through billions of collisions, each one a tiny reenactment of the Big Bang, looking for the statistical fingerprint of gravity leaking away. So far, they have found no clear sign, but their work is far from futile. Each collision constrains the possible size and shape of extra dimensions. The more data we collect, the tighter the cage becomes around the unknown. The energy thresholds at which new physics must emerge grow ever higher. Somewhere beyond the reach of today's machines, the bulk still waits. Meanwhile, the universe itself performs experiments on our behalf. Gravity does not only live in laboratories or accelerators, it rules the cosmos. The motion of stars, the bending of light, the rippling of space-time through gravitational waves, all are arenas in which extra dimensions might reveal themselves. When two black holes merge, the energy released in gravitational waves is so immense that for a brief moment it outshines every star in the observable universe combined. If gravity can escape into the bulk, some fraction of that energy might vanish from our brain entirely, changing the amplitude or frequency of the waves we detect. Since 2015, the LIGO and Virgo observatories have recorded dozens of such events. The patterns match Einstein's predictions with astonishing precision. Yet in every waveform, scientists search for tiny deviations, delays, echoes, or missing energy that could betray the influence of higher dimensions. None have yet been found, but the detectors are still young. The next generation, including the space-based LISA observatory, will be sensitive enough to hear the faintest tremors from across the cosmos. If the bulk ever speaks, they will be the first to listen. The search extends to the largest scales of all, the expansion of the universe itself. Cosmologists measure how fast distant galaxies move away from us, using Type Ia supernovae as standard candles. These cosmic explosions, visible across billions of light-years, allow us to trace the history of cosmic acceleration. The data show that the universe's expansion is speeding up, driven by a mysterious form of energy we call dark energy. But in the Brane-World picture, dark energy may not be a substance at all. It could be the effect of gravity leaking into the bulk, or of bulk curvature pressing back on our brain. In this model, the universe accelerates because it is being gently stretched along an unseen dimension. The force driving the expansion is geometric, not energetic. Astronomers test this idea by comparing the brightness and distribution of galaxies at different epochs. They look for subtle patterns in the cosmic microwave background, tiny fluctuations that reveal how the universe's expansion rate has changed over time. So far, the data can be explained both by dark energy and by extra-dimensional geometry. The two possibilities remain in a delicate balance, each capable of describing the observed acceleration. The key to breaking this degeneracy lies in precision. Future telescopes, such as the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, will probe the early universe with unprecedented clarity. They will map the structure of space itself, perhaps revealing whether cosmic acceleration is truly universal or varies with scale, a clue that might expose the influence of the bulk. But beyond all the mathematics and machinery, there is something deeply human in this pursuit. The search for extra dimensions is a reflection of our own curiosity, our refusal to accept the visible as the whole. It is the continuation of a journey that began when our ancestors looked up at the stars and wondered what lay beyond the horizon. Today, the horizon has moved inward, into the very structure of space and time. Each experiment, from the torsion balances that weigh the unseen to the particle colliders that recreate creation, is a manifestation of that same impulse to reach beyond the limits of perception. Whether the hidden dimensions are found tomorrow or never, the act of searching changes us. It teaches us humility before the vastness of the unknown, and faith in the power of reason to illuminate it. And yet, for all our precision, there remains an unspoken possibility that gravity's leak is not merely outward. The bulk may not be a void into which energy disappears, but a resonant field that responds. If gravity flows out, perhaps it can also return. Perhaps the universe is not losing energy but exchanging it, engaged in a cosmic dialogue with higher dimensional space. If that is true, then every black hole merger, every gravitational wave, every expansion of the cosmos could be part of that conversation. A two-way communication between the brain and the bulk. To explore that possibility, we must follow gravity beyond the boundary of our universe and ask what echoes might come back. When scientists first imagined that gravity could leak into higher dimensions, they thought of it as a one-way journey, energy escaping silently into the unseen. But the universe rarely tolerates one-way motion. Every wave that leaves must encounter resistance. Every echo must find a surface. If gravity can flow into the bulk, then the bulk itself must respond. The result is something extraordinary, a higher dimensional mirror, that sends whispers back into our world. The idea of bulk feedback began as a mathematical curiosity. In the late years of the 20th century, when the Randall-Sundrum models described a warped fifth dimension, physicists realized that the equations of general relativity could not stop at our brain. The gravitational field extended into the bulk, curved by the presence of our universe. The curvature, in turn, influenced the brain again, creating a feedback loop. Space was not passive, it was alive with response. This interaction is delicate and complex. To understand it, imagine our universe as a thin, elastic sheet floating in a vast ocean of invisible water. When a massive object forms on the sheet, a star, a galaxy, or a black hole, it presses downward, sending ripples into the water below. Those ripples spread outward through the bulk, bending as they encounter its curvature, reflecting from its boundaries, and eventually returning to the sheet. When they do, they create secondary ripples, faint, delayed distortions that alter the original pattern. In our universe, these returning waves manifest as tiny modifications in gravity's behavior. The equations describing this are elegant but unforgiving. They suggest that what we experience as cosmic acceleration, or as invisible mass, might be the returning pressure of the bulk's curvature on our brain. In other words, dark energy and dark matter could be the echoes of our own gravity, resonating through higher space. Consider a black hole merger, one of the most violent events known. Two titans of space-time spiral toward each other, warping the geometry of the cosmos itself. When they collide, they release a storm of gravitational waves, a symphony of curvature that ripples outward in every direction. In a purely four-dimensional universe, those waves would travel forever, fading only with distance. But if the bulk exists, part of that storm escapes into it, leaving our brain with slightly less energy than predicted. Those bulk waves do not vanish. They travel through higher space, following the curvature shaped by our universe. Some may dissipate, but others reflect or refract, guided by the geometry of the fifth dimension. Eventually, a portion might return, crossing back into our brain as a faint echo, a ripple that arrives seconds, minutes, or even years after the main event. To our detectors, it would appear as a subtle aftershock in the gravitational signal, a soft murmur following the roar. Scientists have begun to search for exactly these patterns. In the data from LIGO and Virgo, they look for secondary pulses, small deviations from the expected decay of gravitational waves. The process requires immense care. The data are filtered for noise, calibrated against seismic and thermal fluctuations, and compared to precise numerical simulations of Einstein's equations. Any deviation could be the first sign of communication across dimensions. A few events have shown curious features, tiny echoes within the noise, statistically ambiguous but tantalizing. They may be nothing more than instrumental artifacts, or they may be the first whispers of the bulk answering back. No one knows yet. But the search continues, and with each new detection, the sensitivity grows. The upcoming LISA mission, orbiting the Sun itself, will listen for gravitational waves 1,000,000 kilometers apart, capable of detecting bulk feedback if it exists at all. The concept of feedback extends beyond individual events. It may shape the entire history of the cosmos. The expansion of the universe could be a form of slow resonance, a breathing of space-time driven by the exchange of gravitational energy between the brain and the bulk. When energy leaks out, space expands. When the bulk presses back, it accelerates. The balance of this exchange might determine the ultimate fate of the universe. If this is true, then dark energy is not a mysterious force, but the reflection of our own gravity upon the higher dimensional mirror. The universe expands because it is being gently pulled by its own echo. The bulk acts like a resonant chamber, amplifying certain modes of curvature while damping others. Over billions of years, this resonance shapes the evolution of everything: galaxies, cosmic voids, even the rate at which time itself flows. In this framework, the cosmos is not a closed system, but an instrument. Each massive event, Each gravitational wave is a note played upon the strings of higher space. The bulk responds in harmony, creating a cosmic feedback loop that sustains the melody of existence. To the human mind, this is an almost spiritual vision, a universe that listens to itself, that resonates with its own geometry, that remembers every vibration it has ever made. The implications extend even further. If multiple branes exist within the bulk, their gravitational fields could interact through this same feedback mechanism. A supernova on one brane might send gravitational waves through the bulk, which then influence the structure of a neighboring universe. Those universes could, in turn, echo back, subtly shaping the distribution of matter in ours. The result is a gravitational web of communication linking countless worlds, each unaware of the others, except through the pull of shared geometry. This idea offers a radical explanation for dark matter. The missing mass that keeps galaxies spinning faster than their visible stars can account for could be the gravitational influence of matter on nearby branes. Its pull reaches us through the bulk, shaping the orbits of stars and the motion of clusters, yet it emits no light because it exists in another universe entirely. What we call dark matter may be the presence of another cosmos pressing against ours. Some cosmologists take this further still. They imagine that the entire multiverse is a single, interconnected system of branes, all coupled through the bulk. The geometry of one influences the others. A collapse in one universe might trigger expansion in another. The birth of our cosmos could have been the echo of a collapse elsewhere, the rebound of a higher dimensional wave. If so, then the Big Bang was not the beginning, but a response, a bulk feedback event on the grandest possible scale. The collision or vibration of neighboring branes sent energy surging into our universe, igniting matter and time. Even now, faint remnants of that first echo may linger in the cosmic microwave background, written as subtle asymmetries in its pattern. Scientists have begun to search for such signatures, mapping the sky with instruments of extraordinary precision. They look for circular anomalies, cold spots, or regions where the polarization of the cosmic background light twists unexpectedly. A few features have sparked debate: too large, too coherent, too strange. Perhaps they are random. Perhaps they are fingerprints left by the bulk's influence. The beauty of the bulk feedback hypothesis lies in its unity. It explains multiple mysteries: the weakness of gravity, the nature of dark matter, the acceleration of cosmic expansion, through a single concept, that our universe interacts with higher dimensional space. Instead of adding invisible particles or mysterious energies, it adds geometry. The complexity of reality reduces to the curvature of the unseen. Yet even as equations evolve and data accumulate, something deeper emerges from this picture: a sense of participation. We are not passive observers of the universe. We are part of the feedback loop. Every act of measurement, every gravitational wave we detect, every idea we form about the structure of space contributes to the resonance. The universe is not just around us, it is through us, communicating in ways we have barely begun to hear. When you stand beneath a clear night sky, surrounded by silence, you may imagine the universe as still, but it is not. It vibrates constantly, a sea of gravitational motion. Every black hole that merges, every neutron star that quakes, sends ripples through the bulk. Some of those ripples will, after eons of travel, wash over our brane again, slightly altered by their journey. Perhaps, in that gentle tremor, the universe remembers itself. If this vision is correct, then we live within a hall of mirrors, each brane reflecting and refracting the others through the bulk. Gravity is the light that travels between them, carrying information, shaping structure, weaving connection. Our world is one reflection, among countless others, bound together by the same higher dimensional resonance. To study gravity, then, is to listen, not only to what our universe says, but to what the others whisper back. We are the latest ears in a chorus of dimensions, interpreting the echoes of eternity. And so, the story continues. The next step in our search leads beyond feedback into the full architecture of the multiverse, a realm where brains drift like continents upon the ocean of the bulk, and where gravity is the only bridge between them. Imagine standing at the edge of a great ocean. The horizon stretches endlessly, yet beyond it lie unseen lands, each shaped by its own tides and storms. Now imagine that the ocean itself exists not in 3 dimensions, but in many, a boundless sea of higher dimensional space. Within this sea drift the brains, each one a self-contained universe. Some are flat and calm, others curved and turbulent, some expanding, some contracting. Together they form the multiverse, not a collection of isolated bubbles, but a vast, interconnected structure floating in the higher dimensional bulk. Our universe may be one such brain, a luminous membrane carrying stars and galaxies across the surface of the bulk. The other brains could be near or far, parallel or angled, depending on the geometry of higher space. Though we cannot see them, their gravitational influence may pass through the bulk, touching our world with faint, invisible hands. Every galaxy in our sky might feel the pull of unseen neighbors drifting through the higher dimensional deep. The notion of a multiverse is not mere speculation. It arises naturally from the mathematics of string theory and M theory, where the solutions to the equations describing spacetime are not unique. There are countless stable configurations of the compact dimensions, each one giving rise to different physical laws, different particle masses, different constants of nature. In this sense, each brain represents a separate realization of the same underlying geometry, a different verse in the cosmic poem. The landscape of possible universes is vast beyond comprehension. Some physicists estimate the number of distinct Calabi-Yau shapes at more than 10 to the power of 500. Each corresponds to a different way the extra dimensions can fold, producing a unique universe with its own physics. Our cosmos is one of them, a specific melody chosen from an unimaginable symphony. The multiverse, then, is not a fantasy, but the inevitable consequence of the mathematics itself. In this grand vision, the bulk is the stage upon which all universes perform. It is not empty, but filled with curvature, energy, and structure. Brains drift through it like sheets of light, occasionally colliding or resonating with one another. When they collide, immense bursts of energy are released, capable of creating entire new universes. Such collisions might explain the origin of our own, the event we call the Big Bang. In the ekpyrotic model, our universe was born not from a singular explosion, but from the impact between 2 brains. Before the collision, time as we know it may not have existed. The moment of contact unleashed a firestorm of energy, heating our brain and filling it with radiation and matter. As the brains recoiled and moved apart, our universe expanded and cooled, eventually forming stars, galaxies, and life. The afterglow of that collision still surrounds us today, visible as the cosmic microwave background. This interpretation reframes the most fundamental question of cosmology. Why did the universe begin? Instead of asking why something emerged from nothing, we ask how one brain met another. The origin of everything becomes an event in higher dimensional space, governed by the geometry and motion of the bulk. The Big Bang is no longer the beginning of all things, but a transformation within a larger continuum. If this is true, then other universes may be forming all the time, born from collisions elsewhere in the bulk. Some may last only moments before collapsing, others may endure for billions of years. The multiverse becomes an ecosystem, a living field of creation and decay, where the geometry of higher space continually gives rise to new realities. Within this framework, gravity plays a central role. Because it alone can move through the bulk, it acts as the mediator between brains. The gravitational fields of nearby universes can influence one another, subtly warping the curvature of the bulk. These interactions could explain phenomena that appear inexplicable within a single universe, the mysterious alignments in the cosmic microwave background. The large-scale structure of the cosmos, and even the acceleration of expansion may all be manifestations of gravitational resonance between branes. The idea of a multiverse also offers a new way to understand fine-tuning, the apparent coincidence that the constants of nature are precisely suited for life. In a single universe, this seems miraculous, but in a multiverse, it is inevitable. If there are countless universes, each with different physical laws, then at least one will have the conditions necessary for life to emerge. We exist in that one because we could exist nowhere else. What seems like design is simply selection, a natural outcome of infinite variety. Still, the implications are profound. If the multiverse is real, then our universe is not unique. It is part of a greater whole, one branch of a cosmic tree whose roots lie in higher dimensional geometry. Each brane is a leaf upon that tree, and gravity is the sap flowing between them, carrying information, energy, and curvature through the bulk. Some scientists have proposed that we might one day detect these neighboring universes indirectly. If a nearby brane passes close to ours, its gravitational influence could leave subtle marks in our cosmos. The cosmic microwave background might show unusual cold spots or distortions, evidence of another universe brushing against our own. There have been hints of such patterns, circular regions where the temperature fluctuations deviate from the norm, though none yet confirm a collision. Still, the search continues, as each new map of the early universe reveals more of its intricate structure. The bulk itself remains mysterious. It is not simply empty space, but a higher dimensional manifold governed by its own equations. In some models, it has curvature that focuses gravity toward the branes, keeping them stable. In others, it may be flat, allowing branes to drift freely. Its properties determine everything: the shape of the universes it holds, the strength of gravity, the evolution of time. To understand the bulk is to understand the architecture of existence itself. The multiverse concept also invites a deeper reflection on what it means to observe. Every measurement we make is confined to our brain. Light, matter, and electromagnetic radiation cannot leave it. We are like inhabitants of a single world among many, seeing only our sky and mistaking it for the whole. The other branes could be only a microscopic distance away, separated not by space, but by dimension. Yet we cannot reach them, for we are bound by the geometry of our universe. Still, gravity offers a bridge. Through it, we might sense the presence of the others. Their gravitational fields may ripple through the bulk and into our world, subtle yet detectable. The dark matter that shapes galaxies could be such a bridge, the gravitational fingerprint of a neighboring brane. In this view, the cosmos is not isolated but communal. Every brane affects every other, directly or indirectly. The bulk weaves them together, making the multiverse a single continuous entity. It is a universe of universes, bound by geometry, connected by gravity, and driven by the endless interplay of dimensions. If gravity is the messenger between branes, then geometry is the language it speaks. The curvature of the bulk tells gravity how to move, and gravity tells the branes how to curve. In that dialogue lies the story of creation itself. As our understanding deepens, the boundary between physics and philosophy grows thin. The multiverse is not a speculative dream, but a logical extension of the equations that describe our world. It is the natural consequence of taking geometry seriously, of admitting that space and time may have more directions than we can perceive. And yet, for all its grandeur, the multiverse also humbles us. It reminds us that our universe may be one small note in a cosmic chord, one ripple in an ocean of infinite depth. The night sky, with its billion galaxies, may represent only a fragment of reality. Beyond it lies the bulk, vast, silent, and filled with unseen worlds. To understand what connects all of this, we must return to the foundation, gravity itself. For gravity is not merely a force within the universe. It is the shape of the universe, the geometry of existence. To grasp its full meaning, we must look beyond even the multiverse and into the heart of geometry itself, the source of all curvature, all motion, and all being. Einstein taught us that gravity is not a force but a form of geometry. Space and time curve around matter, and matter moves along that curvature. The planets circle the sun not because an invisible hand pulls them, but because the fabric of space-time itself bends beneath the weight of the sun's mass. For a century, this vision has shaped our understanding of the cosmos, yet it may describe only the surface of a deeper reality. If higher dimensions exist, then the geometry of the universe extends beyond four-dimensional space-time. What we call gravity could be the shadow of curvature in a larger structure, the imprint of higher dimensional geometry projected into our brain. The mathematics of the Brane-World model makes this precise. When Einstein's field equations are extended into 5 dimensions, new terms appear when we project them back onto our 4-dimensional universe. These terms mimic additional energy sources, altering the behavior of gravity. They can act as if space contains a cosmological constant, as if unseen matter exerts a pull, or as if the universe itself accelerates. In this way, dark energy and dark matter might not be substances at all but geometric effects. The influence of curvature in the bulk upon our brain. If this interpretation is true, then gravity is not weak, it is wide. Its field lines spread through all dimensions, carrying information about the shape of the bulk. Every gravitational field we measure is a message from higher dimensional space. The orbits of planets, the bending of starlight, and the waves that ripple from merging black holes are all fragments of that message, translated into the language of 4-dimensional space-time. To grasp this, imagine that our universe is a curved sheet stretched within a larger space. The curvature of the bulk pushes and pulls on this sheet, shaping its contours. Every valley corresponds to attraction, every ridge to repulsion. What we experience as gravitational acceleration is simply the motion of objects sliding along these contours, following the geometry carved by unseen dimensions. In this view, geometry replaces force entirely. Space tells matter how to move, and the bulk tells space how to curve. The entire cosmos becomes a dynamic sculpture, molded by invisible dimensions. Gravity, electromagnetism, and even the quantum fields that fill space may all arise from the same geometric foundation. The differences we perceive between forces could be illusions caused by how higher dimensional curvature projects onto our limited perspective. Einstein's equations themselves hint at this unity. Their structure is universal. They can be written in any number of dimensions. In 5 or 10 or 11 dimensions, they still describe the relationship between curvature and energy. When we reduce those equations to 4 dimensions, the additional components manifest as new fields or forces. What seems like diversity in physics may be the simplicity of higher dimensional geometry viewed from within. This geometric picture also changes how we understand the passage of time. In relativity, time is one coordinate among others, its flow determined by motion and curvature. In higher dimensional theories, time may emerge from geometry itself, a pattern formed by the way brains move through the bulk. The expansion of the universe could be the stretching of our brain along a hidden direction, the ticking of cosmic time, a measure of how it evolves through higher space. Such an idea transforms cosmology into a branch of geometry. The fate of the universe depends not only on the matter it contains, but on the curvature of the dimensions beyond it. A small change in the shape of the bulk could alter the entire history of our cosmos, its rate of expansion, its eventual collapse or acceleration, even its capacity to host life. Mathematicians studying Calabi-Yau spaces have shown that tiny variations in their geometry can produce enormous differences in physical law. A slight twist in one of the hidden dimensions could change the strength of gravity, the mass of particles, or the stability of atoms. Our existence, then, depends on the precise shape of spaces we can never see. The universe we know is carved by the geometry of the unseen. At its deepest level, the concept of gravity as geometry connects to an even more fundamental idea, that space itself may not be continuous. Quantum gravity suggests that at the smallest scales, space-time is made of discrete units, like the pixels of a vast holographic image. The curvature we call gravity may emerge from the collective behavior of these microscopic elements, just as temperature emerges from the motion of atoms. In this sense, the bulk could be the ultimate hologram, a higher dimensional code from which our entire universe is projected. This holographic view finds its most precise form in the principle known as ADS-CFT correspondence. It states that a theory of gravity in a curved higher dimensional space can be equivalent to a quantum field theory without gravity on its boundary. What happens inside the bulk is mirrored perfectly by information on the surface. Geometry and quantum mechanics, long thought irreconcilable, become two sides of the same coin. If this principle holds universally, then our four-dimensional universe might be the holographic boundary of a five-dimensional bulk. Gravity's behavior within our world would reflect the quantum processes taking place at the edge of higher space. The curvature we feel as gravity would be the shadow of quantum information flowing through dimensions beyond sight. This unity between gravity and geometry hints that the universe is self-consistent at every scale. The quantum vibrations of strings and the curvature of space-time are not separate phenomena, but expressions of the same underlying structure. The weakness of gravity, the hierarchy of forces, and even the acceleration of the cosmos may all be encoded in the geometry of the bulk. The realization is both humbling and empowering. It tells us that by studying gravity, we are not merely observing a force, but uncovering the architecture of reality. Every experiment, every equation, every observation of a distant star is a step toward decoding the blueprint of existence itself. In this geometry, everything is connected. The motion of a planet, the spin of an electron, the expansion of the cosmos, all are threads in a single mathematical tapestry. The universe is not built from matter, but from relationships, from the curvature and connection of dimensions. We stand, perhaps unknowingly, at the center of that geometry. Our consciousness arises from the same structure that shapes the stars. The fabric of everything, matter, energy, and thought, may be woven from the same higher dimensional pattern. But if gravity is a shadow of higher geometry, then what casts that shadow? What lies beyond the bulk itself? The final step in this journey takes us there, into the idea that our universe, with all its forces and dimensions, may itself be only a projection, a reflection of an even higher reality, a realm where geometry and existence are one and the same. There is a quiet moment that comes when one realizes that gravity may not be what it seems. It is not merely a force pulling objects together, nor even a curvature that shapes motion. It may be a shadow, a whisper from a deeper realm. Every orbit, every fall, every ripple of space-time could be the echo of something happening beyond the boundaries of our perception. In this vision, the universe becomes a hologram, projected from a higher dimensional reality. The patterns we see in space and time are not the totality of existence, but the visible surface of a grander geometry. Just as a three-dimensional object casts a two-dimensional shadow, the bulk of higher dimensions could be casting our universe as a four-dimensional image. Dynamic, self-consistent, yet fundamentally derived from a deeper source. If gravity is the curvature of space-time, then perhaps space-time itself is the curvature of something higher. The equations of string theory and M theory hint at this continuously. They describe a universe where every particle, every field, and every force emerges from vibrations in an underlying structure of geometry. The world we inhabit is a pattern, and the pattern itself is information. In the holographic picture, all the information that describes our universe might be encoded on a distant surface, a cosmic boundary at the edge of the bulk. We live within that projection, experiencing reality as if it were three-dimensional, though its true description may lie elsewhere. The geometry of higher space writes itself into our cosmos as gravity, light, and matter. This idea does not diminish reality, it deepens it. To call the universe a projection is not to call it unreal, but to suggest that what we perceive is a translation of something even more fundamental. The laws of physics, the constants of nature, and the structure of space-time are the vocabulary of this translation. Our existence becomes the manifestation of higher geometry, expressing itself in the language of energy and motion. Such a universe is profoundly interconnected. The boundary and the bulk mirror one another perfectly. Every vibration in one reflects in the other. The ripples we call gravitational waves might have counterparts beyond our universe, waves in the deeper reality that sustain our own. The birth of stars, the collapse of black holes, the very flow of time itself might all be echoes of movements in the higher realm. In this framework, the question of why gravity is weak gains new meaning. Gravity is not diluted energy, it is translated geometry. It spreads across all dimensions because it is the universal link between them. The weakness we measure is not a flaw but a sign of depth, the faint signature of a force that connects our brain to the entire structure of existence. The sun's light, the orbit of planets, the falling of an apple. Each of these ordinary events becomes profound when seen through this lens. They are the surface ripples of a higher dimensional tide. The apple falls not because it is pulled, but because it follows the curve of geometry shaped by dimensions we cannot see. We do not live in space. We live in its shadow. The holographic vision also provides a new way to think about consciousness. If reality itself is a projection of higher dimensional information, then consciousness, the act of observing and understanding, may be part of that same process. Our minds could be local expressions of the universe's attempt to perceive its own geometry. Awareness might be the reflection of higher order structure within the folds of space and time. Physics and philosophy converge here. Geometry becomes ontology, the study of being itself. The universe is not made of matter, but of relationships, connections, and symmetries. Matter is geometry that vibrates. Energy is geometry that moves. Time is geometry that changes. Everything that exists is a pattern in the curvature of higher dimensional space. When we look at the stars, we are seeing the projection of this geometry into our limited perception. Each photon of starlight is a messenger from the curvature of the bulk, carrying encoded information about the higher structure from which it emerged. To understand the universe fully is to decode that geometry, to read the shadow and infer the shape of what casts it. In this sense, the pursuit of science becomes an act of revelation. Every equation, every observation, every experiment is a translation between shadows and the light that creates them. The discovery of higher dimensions would not destroy our understanding of the universe. It would complete it. It would reveal that we have been studying the silhouette of a grander reality all along. The implications reach beyond physics. If the cosmos is a projection, then perhaps every universe is, each one an expression of a deeper whole. The bulk may be an infinite expanse of geometry, eternally creating brains that bloom into universes, each with its own version of time, matter, and law. Our universe is one such bloom, a single petal in an infinite cosmic flower. And gravity, soft, persistent, universal gravity, is the scent that all petals share. It drifts through the bulk, connecting everything, carrying information from one universe to another. It is the one force that transcends boundaries, the one language that all realities speak. Perhaps this is why gravity feels different from the other forces. It cannot be confined because it belongs to the whole. It is not a field among fields, but the echo of the total geometry of existence. Every gravitational wave, every orbit, every fall is a moment of communication across dimensions, a reminder that we are part of something vast and unified. In the end, the search for extra dimensions, for brains and bulk, for the ultimate origin of gravity, leads us to a simple but profound realization. The universe is not an isolated system, but a geometric manifestation of a deeper order. The weakness of gravity is the strength of connection. Its silence is the whisper of infinity. Perhaps the bulk itself is not beyond us. Perhaps it is the true reality, of which our universe is only a visible fold. The forces we feel, the stars we see, the thoughts we think, all are patterns within a larger fabric. To glimpse that fabric, even for a moment, is to see that gravity is not a force at all, but a message. One written in the language of geometry and carried across dimensions. And so the story ends where it began, with a magnet lifting a paperclip against the pull of an entire planet. What seems weak may, in truth, be vast. The faintest force in our world may be the most powerful in the multiverse. Its reach extends through dimensions unseen, binding every brain, every star, every shadow of reality into one coherent whole. Perhaps gravity is not the mystery, but the messenger. Perhaps the universe itself is the message. Every orbit, every fall, every whisper of space-time is the echo of a higher realm. And every time we feel gravity's pull, we are touching, however faintly, the edge of eternity.